You've seen those drone light shows, right? Hundreds, sometimes thousands of tiny robots just painting these incredible pictures in the night sky, all moving in perfect harmony. Or think about satellite constellations, all working together to wrap the entire globe in connectivity. It's this amazing magic of synchronized machines, a magic that hinges on every single member of the team doing its job perfectly. But that leads to the big question, doesn't it? What happens when one of those drones glitches out, or a satellite's motor just fails? You see, in a system where everything is so tightly connected, one tiny little error can have absolutely massive consequences. And believe me, this isn't just some what-if scenario, it's one of the single biggest challenges for the future of robotics. So to really get why this is such a big deal, we need to talk about something called multi-agent systems. Now, that's the fancy technical term for these teams of robots or even software programs that work together. They're incredibly powerful, for sure, but that very interconnectedness, well, that's also their greatest weakness. So what exactly is a multi-agent system, or MAS for short? Just think of it as any team of independent agents that are all communicating and cooperating to get a job done. It could be a whole fleet of delivery drones, a network of sensors monitoring the environment, or even a team of rovers exploring Mars. The key here is teamwork, all driving toward one common goal. And here is where it gets scary, because all these agents are linked up, talking to each other. A fault in one agent doesn't just stay with that one agent. Nope. It can spread like a virus, jumping from one to the next, corrupting its neighbors, and potentially bringing down the entire system. The stakes couldn't be higher. Now, for years, engineers have been wrestling with this exact problem, and they've basically come up with two main philosophies for making these systems fault-tolerant. In other words, able to handle failures without falling apart. So let's take a look at these classic approaches. The best way to think about it is the tank versus the acrobat. On one hand, you've got passive control. That's the tank. It's built super tough, pre-programmed to handle a very specific list of things that might go wrong. It's incredibly robust, but if a surprise comes along, something it wasn't designed for, it just can't adapt. Then you've got active control, the acrobat. It's nimble, constantly watching what's happening and changing its strategy in real time. But all that agility comes with a price. It can get completely thrown off by a weird fault it doesn't recognize, or even just by too much random noise from the environment. So you're stuck with this tough choice, right? A system that's strong but rigid, or one that's agile but kind of fragile. But what if you could have both? What if you didn't have to choose? Well, that's exactly what some new research is proposing with a method called Hybrid Fault-Tolerant Cooperative Control, or HFTCC. And the idea, in concept, is brilliantly simple. Just merge the two philosophies. Create a system that has the built-in toughness of the tank, but also the real-time smarts of the acrobat. This hybrid approach is all about getting the best of both worlds, creating a swarm that is both fundamentally tough and intelligently adaptive. Okay, so how does it actually pull this off? Well, HFTCC really boils down to 4 key steps. First, you have a really robust observer. Think of it as a spotter that is constantly watching the whole system. The spotter is part of that passive tank side, so it's really good at seeing through all the outside noise. Second, when a fault actually happens, that spotter pinpoints exactly what went wrong. Third, that fault data gets sent right to the system's controller. Let's call that the brain. And finally, the brain uses that fresh information to adapt on the fly, just like our acrobat. There are a few really clever innovations that make this whole thing tick. That spotter is technically something called an unknown input observer, and it's specifically designed to ignore all the distracting environmental noise and just focus on finding real faults. Then the adaptation part. It's not a complete system reboot. It's a much more streamlined process called fault accommodation. And maybe best of all, the whole design is distributed. Each little agent helps monitor its neighbors, which spreads out the workload and makes the whole system run way more efficiently. I know, this all sounds great in theory, but the real question is, does it actually work? While the researchers put HFTCTC through its paces in a really detailed computer simulation to see exactly how it would hold up under pressure. So here's the setup for the test. A simulated swarm of 7 communication satellites, flying in 2 different groups. Then, in the middle of the simulation, they hit 2 of those satellites with sudden actuator faults, a really common type of hardware failure. The big question, of course, is, how does the system react? The results were, frankly, staggering. Just look at this chart. It's comparing the total system error of a purely passive tank system versus the new hybrid HFTCC system right after the failures hit. You can just see it. The error in the old passive system is huge, while the HFTCC system barely even flinches. But let's get into the actual numbers. First up, root mean square error. Now that's basically a measure of the system's average wobble, how much it deviates from where it's supposed to be over time. The HFTC method cut this constant ongoing error by an incredible 61.55%. I mean, that is a massive improvement in the system's overall stability.
Okay, but what about that initial shock, that big jolt right when the fault happens? Well, the HFTCC system slashed the maximum error spike, that big initial wobble, by almost 49%. So it doesn't just perform better over the long haul, it handles the immediate crisis way, way better.
So, the errors are a lot smaller, but how quickly does the team get back on track? That's what the researchers call convergence time. And as you can see in this table, the agents using HFTCC were able to regroup and get back to their mission in about half the time it took the old passive system. They're not just more stable, they recover so much faster. And you don't have to just take my word for it. The researchers themselves summed it up perfectly in their conclusion. Their findings show not just a tiny improvement, but a substantial enhancement and a remarkable reduction in error. This isn't just a little tweak, it is a huge leap forward. So, what does a breakthrough in controlling a few simulated satellites mean for you and me? Well, this research has enormous implications for the increasingly autonomous world we're all building day by day. The big takeaway here is that this hybrid approach lets us build teams that are both smarter and tougher at the same time. And that translates directly into safer, more reliable systems. Systems we can actually depend on to do critical jobs. This is a vital piece of the puzzle for the future of, well, everything. From drone deliveries and fleets of self-driving cars to those long-term space missions where failure just isn't an option. And that really brings us to the final critical question. As these autonomous teams of robots and AIs become more and more a part of our daily lives, managing traffic, delivering packages, exploring new worlds, the question of reliability really becomes a question of trust. Innovations like HFTCC are a massive step in the right direction, but they also force us to ask a much bigger question. What is it going to take for us to truly, deeply trust our autonomous creations?